Hello everyone. Today we will see how basically distributed training is actually carried out on a cluster, right? And the theory portion which we have discussed talks about how we are going to implement distributed training, and ultimately we will be in a position to come up with scalable AI systems. So the environment in which I am executing my workloads today is on a cluster which I have logged in using SSH, right? And that is basically a NVIDIA DGX server, okay, which has now got this system information, and I would be using this particular setup for this particular week's explanation of whatever theoretical we have covered till now and the hands-on which I am going to cover today. So now this particular system is actually a H100 server, and let's try to understand and see the system's configuration. Till today, I have worked on my laptop, which basically was intentionally done to give you people a feel of how a GPU could be used for developing AI applications, how Dockers could be used, how Kubernetes would be used. All of that was to show you basically so that you can use it on your own laptops. Now, this particular week, we are trying to work on this specific H100 cluster. So let us try to see the configuration of this. So if I do NVIDIA SMI, I would be able to see that this is having 8 GPUs, right? H100 GPUs. See, NVIDIA H100, GPU number 0, GPU number 1, GPU number 2, 3, 4, 5, 6, and 7. So this way, we see that this is a DGX H100 cluster with 8 GPUs with 80 GB memory each. Okay, so now this basically confirms that we are working on a multi-GPU system for this week, right? And now let me just show you what all we have got to see as a demo after we have gone through the theory on distributed training till now. So we have got about 6 programs, out of which I will explain and discuss and execute these apart from Horoward, because Horoward is a different way of achieving the same thing which we are trying to do. Okay, and it actually has a different type of a setup, which on this cluster of ours we have not done it. But if you people are interested, you can always do Horoward installation for your cluster for distributed training, right? So now this is how basically is the setup, right? And now let us try to restrict ourselves, okay, for this demo to utilize only 2 GPUs. Okay, so now tomorrow when you start working on such a system, you would actually be required to be using, right, number of GPUs which you want, right? So you can sometimes require 2 GPUs, you want sometimes 4 GPUs, you can require sometimes about 8 GPUs, so on and so forth, right? So based on however number of GPUs you want, you actually can visualize those number of GPUs and use only those, right? So let us try to see how we can do that, right? So one of the commands which we use for doing it is this, okay? So this shows the CUDA visible devices, okay? And what I'm trying to do is I am trying to actually see, okay, how many devices I can work with. So I can actually run these with whatever devices I want. Okay, and um, if I now see this, okay, I need to export. Okay, first let us say without export, if I do, let me see the count of the GPUs here. So I use this command, right? And it will tell me what type of PyTorch I'm using, okay, and whether the CUDA is there or not, what is the build, and it will tell me the GPU count, which is 8, right? So these are NVIDIA H180 GB HBM3, HBM3. So these are 8 GPUs, right? So 0, 1, 2, 3, 4, 5, 6, 7, and 8, right? Now I restrict myself only to 0 and 1, okay? So what I do is, so I again use this type of a command basically just to export and see, okay? The idea is just to not type the okay, so now I just export, okay, this command, use this command export CUDA visible devices 0 and 1, and now when I see, okay, the same thing of how many GPUs I am allowed to use, okay, I should be in a position to see GPU count as 2. So if I use, let us say, 0, 1, 2, and 3, okay, so now I am locked to use 4 GPUs, right? So this is how basically you can restrict yourself to the number of GPUs which you want to use. So at present we will only use 2 for this setup of ours, and that is the reason why we are seeing these 2 GPUs here, right? Now let us try to actually go to our first program, which is a single GPU baseline program. So let me just go to that, okay, program, and then see what is this program. We will discuss this program and then we'll run this program, okay. So this program basically is, let me just show you this program first before I run it, and then we can run it and see what it is, okay. So if you go and see this program actually, okay, this program is a small ResNet program, okay, on cipher 10, okay, and we are just trying to basically do a handful of epochs. The idea here is not to go in with training efficiency, not to understand how accurate it is, but basic idea is to see how we can do distributed training, right? And to be more specific, distributed data parallelism, okay, that is what we are going to actually use, okay. So the basic idea here is that once we distribute it as against when we do it on a single GPU, right, our loss curve should be equivalent, right? The basic idea is this. So now this is what it is. So if you see the things here, there is this model which we are using, which is ResNet 18, and there is this loader concept wherein we are trying to load in the data set, which is cipher 10. Okay, now I have already downloaded it, so no issues with it. But if you use it for the first time, if you don't have the cipher 10 data set, you will have to download it, right? And then you will basically have to use basically this particular thing on a device which basically has CUDA, right? And you are trying to use that, okay, and trying to run this program. So let us try to run this program and see actually what happens in this, and then we would be able to see what actually is happening. So I'm not typing because there are so many things which you can do. Okay, so what I will do is now I will run this program, okay, Yes, which is basically on a single GPU. Okay, so CUDA visible devices is equal to 0, Python 3 baseline program train dot single, okay, dot data basically, okay, and then epochs is 1, batch size is 128 to keep it uniform, right? Let us try to run this program. Okay, so if you run this from here, you will be able to access it correctly. Since I was in that folder, I had to change the path name, so no worries. So this is how it is going to happen, and the information about that is written into the file ckpt single.pt, right? We can visualize it afterwards, okay, or you can see it, but it basically has this value, right, of all of that, okay, and then this is the checkpoint thing. Now let us try to see, okay, and try to understand this particular program and see if we can try to actually do a distributed data parallelism on a single node. So we have a single node with 8 GPUs, right? We don't have a multi-node type of a system here, but we do have a single node with 8 GPUs, right? So of course I have this program which is a distributed data parallel program on multi-node, okay, which I am just giving you. If you have got multiple nodes with you, you have to ask your administrator to basically give you access to multiple nodes and multiple GPUs on it, okay. But whatever is on a single node with multi GPU thing, I am going to run. So I am going to run 01, 02, 04 and 06, okay, of the programs which are here. So let us try to see now 02, okay, and see how basically we can change this single GPU thing into a distributed data parallel model, okay, using PyTorch on a single node but with multi GPUs, okay. So let us try to go to that folder and see this program, okay. And if you go to this program now, which is train, sorry, train, okay. Now here you see single node multi GPU training, okay, with PyTorch distribution. So here we are now trying to launch it on 2 GPUs. So I'm using torch run standalone, and number of procs per node is equal to 2. So we know this concept of number of procs or processes, okay. Train underscore this thing, epochs is 3, per GPU batch size is 128, okay. So what does torch run do? It basically talks about setting up the environment variables, rank, local rank, world size, master address, master port, so on and so forth, okay. So something of these errors which can happen, okay, are also there here. But let us try to understand these 4 or 5 things which are very, very important. One thing is this, which talks about uh, 1 minute. Let me just show you one of the very, very important things which talks about how do you distribute things, right? And then try to basically see this. So, see, one of the things which we should understand here is that only rank 0 writes the checkpoint. So, rank 0 is something which is coordinating among all the other processes, right? So, rank 0 is something which is like a root node or a root process, right? And it only does everything, okay. So, that is one thing. And then this is this train sampler wherein we are talking of distributed SAM thing, okay. So this is a training loop. You talk about this, you talk about the model, this thing, you talk about sum across all the ranks, so the global total, okay. Then there is this sampler which talks about distributed sampler here, okay. So these are certain things which we should know as to how we are going to do that, okay. And then this distributed NCCL is basically a GPU to GPU collective. You can use glue also and glue I told you is from Meta. So this is basically a thing which we can use. So this is a distributed setup here which we are trying to use. Okay, so all of these things are very simple in terms of trying to understand the program. We have not yet given any complex program, but basically tried to give you a flavor of how all of this, right? So the basic idea here for this program is that the distributed data parallelism program starts with one process per GPU, and the NCCL is going to provide high speed communication channel. So each process here owns one GPU and receives a different data set shard. Okay, so we're talking of sharding here. That means the data is split. Okay, and during the back propagation, okay, the DDP all here, the reduced stuff, okay, talks about gradient. So both models basically, okay, copies remain identical. So the basic idea here is of trying to understand this sum across all ranks, right? So everybody sees the same global rank. So this is what is important. So let us try to run this particular program now, okay, and then try to see, okay, we can run it on 8 just to show you, right? We can run that. So let me just clear it so that we will go on to the top and then run this. Okay, so let me just try to see again the point wherein don't go to type because it takes too much of time. And yeah, so here I am trying to run that train underscore DDP PY, okay, on two GPUs, 0 and 1, okay. So if we run this, where is this error? Why? Okay, so I have to come out of that. So if you see this now, it is going to run on, okay, two visible devices, 0 and 1, okay, and it is running the same program, okay, and trying to run it for so many epochs, okay, and it has been written into ckpt underscore ddp dot pt, okay. So afterwards we'll see both the values will be same, the weights will be same, the convergence will be same, everything is same. The only thing, the data distribution happens. So that is how it is, okay. And then what we can do now is that here the output, if you see, okay, is something wherein the per GPU batch size is 64. So we actually work with 128, right? So there are two things which two blocks which are going to be worked on each device. So same is the case, okay. Same global batch size of 128 is supposed to be actually achieved. So now we can do this with actually, let us say, 4 GPUs, right? Let us say 0, 1, 2, and 3, and run this and see what actually happens. Okay, so here instead of 64, we can do 32, okay, and see what actually happens. Okay, so this is just to maintain the uniformity of the data size, right? So this is how it's going to actually happen. And so if you see this, okay, ultimately we are in a position to understand and work with, okay, things wherein we are talking of accuracy, we are talking of so many things, right? The idea is to split, right? I'm not going into why it has taken more time, why this took less time, right? It depends on so many other things of data decomposition, right? How work is spread across all these nodes and the latency of the communication, so on and so forth, right? So all those things matter, but the basic idea here is to make you understand Okay, how PyTorch effectively distributes the workload using very simple syntax, which is not very complicated. It does everything on its own, right? So that is one thing. Now I skip the multi-node thing because here we don't have multiple nodes. We only have one node with 8 GPUs. We do have other GPU DGX, but those effectively are not connected and so on and so forth. But now let us try to understand the all reduced benchmark from 04 program, the fourth program. Okay, and then let us try to see that. So we'll go to 04 thing and see what actually is there in that, and when what does all reduced benchmark basically mean. Okay, so just to show you what it is, it basically is area wherein we are talking to have whatever message, okay, or whatever information is sent between two ranked processes or two processes. Okay, one of the things which we should be understanding here is to only understand this specific thing of all reduced stuff. Where did it go? Yeah. So this is more important. Distribute dot all reduce x comma op equal to distribute dot reduce op dot sum. So this basically means that all reduce thing here, okay, is the communication operation used by DDP to combine all the gradients across all the GPUs, right? So we are using 2 GPUs, 4 GPUs, okay. So all the gradients, right, basically ultimately in the end we are supposed to be doing it. Okay, now let us try to understand this with a different type of example, the same example but running in a different way, wherein we talk about running this. I have to again come out of this, otherwise it will give me error because I had put it in that folder. So what I will do is I will now need to, yes. So what I'm going to now do is I'm going to run this program on 2 GPUs, right? The all reduced benchmark, and see what is the execution, what's the output, and then I'll explain you what it means. Okay. So the basic idea here is what we are trying to see here is the bandwidth, right, which is being used, right? So as and how the message size increases, okay, the bandwidth also increases. So here for two H100 GPUs, since I am taking of this world size equal to 2, okay, so for two H100 GPUs here, the bandwidth, okay, increases, you see, with message size, and it reaches somewhere around 298 GBs at 256 or 2 somewhere around roughly, okay, around 268 MBs. Okay, so this is how it's going to happen. So the basic idea here is when the communication happens, okay, and the bandwidth gradually will required bandwidth will go on increasing, right? So the size of the message, the bandwidth required, this is where the distributed training, okay, is an issue. The bottlenecks start appearing at this point in time, because as and how the message size increases, you try to increase the number of GPUs, the bandwidth required goes on increasing. So this is what it shows. Okay, now let us try to understand this, the last example here, which talks about how do you scale the benchmark, right? So I'll show you that program once, and then we will run that program. Okay, so if this is a scaling program, that basically means here we are trying to do some micro benchmarking for trying to understand the scaling efficiency, right? So the basic idea is for each of these steps, right? for one GPU, right? How much samples it actually processes. Okay, so then there is this setup of ResNet models which we are using. Okay, and synthetic batch we reuse for each step. So now data loading costs actually happens. The basic idea is we are trying to understand how do you actually scale up, right, the sample. So this benchmark basically uses the synthetic data so that the loading thing from the disk, okay, does not affect the result. So here the idea is to compare the throughput of one GPU as against throughput of two GPUs, right? And the basic idea is to understand if it is a perfect scaling, you need to double the throughput if there are two GPUs instead of one, right? So, okay, one caveat here that we need to understand that the synchronization overhead is something which we need to be bothered about, right? So apart from this, we can actually run this program now, okay, and see what effectively happens here, okay. So let me just run that program for you and let us discuss, okay. So I'm going to come out of that folder. So I have to run that now. So, so let me just check on that. Yes. So let me just run on first one device, okay, and then let me run it on two devices and see what actually happens, okay. So there is this one GPU on one node, right? So if you see here, samples per second it has processed is this, and the step time it has taken is 38.7 milliseconds, right? So let us try to do the same program using two GPUs, right? 0 and 1, okay. So see here, so this, if you see here now, okay, so so now this is blocks per node if it is okay. So this basically it has used only 1 minute. Let me just make it to two nodes here. Node per node two. Let's try to understand this. Okay. Okay. So there are various configurations, okay, wherein you can just assume how many words, how many processes in that word. So this is basically, when you discuss MPI, right? You have this COM world, okay, number of processes in that world because they can communicate among each other, so on and so forth. We're not going into the MPI and distributed concept here. The basic idea is that is how it's all related to, okay. Because of the want of time and because out of the scope of this particular course, I'm not covering all of that, but that is related to MPI, right? So that's how it is. So I suppose that is what we wanted to cover in this particular week and this particular hands-on. Okay, we will meet next week. Okay, for trying to develop scalable systems. Yeah. So thank you.